Hi everyone, thanks for coming to my talk and thanks to the Hexacon crew for organizing such a fun conference. I'm really enjoying it so far. Today I'm going to talk about SAML, SAML in the cloud and some interesting attack surface that I discovered while poking at like the different big SAML implementations that are in the wild. Um, a quick intro about myself. I'm Felix. I'm a security researcher working for Google Project Zero, and my main focus is virtualization and cloud security. Before joining Project Zero, I also worked in product security for Google Cloud for a couple of years and as a security researcher at ERNW, a small German security consultancy. I also have a fun side project. I'm the main developer of Wegly, which is a code search tool targeted at security researchers. So if you still find all your bugs by crapping for memcopy in like large C and C++ code bases, you should try out Wegly, especially if you don't want to deal with CodeQL. And if you're already using Wegly and have bugs or feature requests, please come and talk to me. I'm always happy to hear about users. So this talk, today's talk is about SAML, and SAML is like a pretty popular standard for single sign-on. And more specifically, I want to talk about why SAML provides like a large and very interesting attack surface for modern cloud environments. So if you want to like compromise a cloud application or even a cloud provider, SAML is one of like the pieces of technology you probably want to look at. And this attack surface is particularly interesting when you talk about multi-tenant software as a service applications. So if you think about a website like GitHub, Slack, but also like the management consoles of your favorite cloud provider. So something like the GCP console or the AWS console, right? All these are like basically one web application that's shared between like a lot of different tenants. Um, and if you ever interacted with SAML before, you will know it's like an infinite source of signature wrapping vulnerabilities that you can use to like do authentication bypasses and privilege escalations and stuff like that. But today I actually don't want to talk about this. Instead, we're looking like for implementation flaws in the underlying technologies that give you like full access to the underlying operating system. So we want like memory corruptions, we want remote code execution and stuff like that. Um, Let's quickly introduce SAML. So the name stands for Security Assertion Markup Language, and it's like this pretty enterprisey, feature-rich protocol for implementing single sign-on based on XML. And it supports a lot of like different use cases, but in the basic classic browser-based login flow, you have like these three parties, right? Like you have a user and a browser, you have an application that's called a service provider in SAML terms, so think of Slack or GitLab again. And then you have an identity provider, which is like the source of trust for user information. And this could be like Google Workspace, or it could be Azure Active Directory, or like a random server that's somewhere in your intranet. And normally this whole single sign-on flow starts when the user visits the service provider. The service provider noticed that the user isn't logged in yet, so it generates something called a SAML request and redirects the browser to a URL on the identity provider while attaching the SAML request as a parameter. And a SAML auth request is this big XML document that tells the IDP how to authorize, it should authorize the user for this specific application. And then how the identity provider should return the response back to the application. And like the protocol, if you actually look at the RFC, it supports like a lot of like different requirements that you can put into this request, like how the IDP should authenticate the user and all kind of weird requirements. In practice, like no one actually uses that and it's completely ignored. So basically the only thing that the request is good for is to tell the IDP to log the user in. So the IDP gets this request and then they have to authenticate the user in some way. And in the happy path, which is why it's called single sign-on, the user is already authenticated, right? Like they have an active session with the identity provider. So this will be completely transparent to the browser and the only thing you notice is a couple of redirects. But if you're not logged in yet, you have to enter your password or use 2FA or whatever like login mechanism the IDP uses. Once the identity provider then has authenticated the user, it generates a SAML response. And that SAML response contains all the information about the user. it attaches this response to a redirect HTTP request back to the service provider, right? So the user browser gets the response and forwards it back to the service provider. The service provider looks at this response, validates it, and then creates a session for the user who can then use the application. And one thing that's interesting about SAML in the cloud space is that the trust relationship between service provider and identity provider has changed quite a bit over time. So in the old world, where SAML was mainly used like in large enterprises, you have something like this, right? Like you had a single identity provider sitting in the enterprise that was the ultimate root of trust for like the whole environment. And you had like a lot of like single tenant applications also in the internal network that would fully trust this identity provider. So there's like no, like attack surface that's only triggerable by an identity provider is pretty uninteresting in this use case. But now if you talk about SAML in the cloud, what actually happens is you have like these large multi-tenant applications, and a lot of like different companies want to use the same application. And all of them want to use their own identity provider for single sign-on, right? So you want to be able to log in to your GitHub account with your Google credentials or your Azure credentials. So what most of these applications allow you to do is you can configure your own identity provider for your own users. And that changes the game quite a bit, because now the service provider actually has to be worried about malicious identity providers. We trust them in a way, hey, of course they can authenticate these users, but if they get like a shell on our system, it's probably not something we would like to see. And this wasn't really an issue like 10 years ago in more traditional environments. So this is a SAML response, and please don't spend too much time looking at it. Like you can ignore 80% of it, but basically it's like this big XML element called response, and it contains information about a successful login event. So you have something like the status code, which is like success in this case. You have the identity of the issuer, which is the identity provider. You have the target audience, which should be like the service provider, so the application. And of course, you have the user identity, which is the thing everyone cares about, which specifies the username or email address of the person who logged in. And the interesting part here is that like the security critical stuff is actually inside a sub-element called an assertion. So like issuer, audience, and attributes are inside these assertion elements. So I mentioned 2 minutes ago, this stuff gets forwarded by the user's browser, right? And I mean, of course, SAML would be absolutely broken if there's no way to do integrity protection of these responses. Because then you could just like write your own response, pass it forward to the application, and you're logged in as whoever you want to be. So how do you do integrity protection for something like this? You use cryptography. And the great thing about SAML is that they use XML signatures for this. So XML signatures fundamentally operate on like standard public key crypto. Both the service provider and the identity provider can have their own private keys, and in an optimal configuration, the service provider would sign requests and the identity provider signs the responses, and like the other end checks the signatures. In practice, SAML requests are not super interesting, and like not signing them is not that dangerous, right? Like you don't get any large negative consequences out of this, so like no one bothers with signing that. But of course, if you don't sign your SAML response, or your service provider doesn't actually verify these signatures, like you don't have a working auth mechanism, right? It's like very easy to bypass. And it's like, so this is like if you work as a penetration tester, this is kind of the type of bug you find everywhere, because all the people forgot to like click on the checkbox that actually enforces signature validation. For us, the fun part about this is that for like a working setup, XML signature verification is actually part of the unauthenticated attack surface of all the service providers and of many identity providers, right? So if we can find bugs that we can trigger during signature verification, we have quite a nice list of targets that we could attack. So if you are used to modern crypto, you would say, hey, signature verification, that sounds simple and straightforward. Like how can you get an RCE while you do signature verification? So let's introduce the notorious XML-D signature standard, which is like a great example of a security standard that was invented in the early 2000s. So it's super complex, has like a really large attack surface, and you can configure it in a lot of ways, and most of the configurations absolutely break it, right? I think in practice it's so error prone that pretty much every implementation has been broken multiple times in the past and is probably still broken. Like so XML signatures is really bad at actually doing signatures, right? And then it also opens a text surface. So if you want to get rid of a technology, get rid of this one. So how do XML signatures work? You have like the standard, it defines a new XML element called signature, and for like a normal SAML response, you would normally insert that as part of the response element or the assertion child element I mentioned earlier. The signature element then has like three sub-elements: a key info, which specifies, well, it describes the signer key, like who signed the signature. And you can put like a raw key in there. Sometimes you will find certificate in there. Some setups just use a key identifier or something like that. Or like a reference to an URI where you then can find the key. And the important part here is the service provider actually needs to verify that this key is a key they trust, right? So that's the second most typical example where they just forget to do that, and like you can generate a valid signature, but with a private key you control, and you will still be logged in. And then you have the signature value, and as the name suggests, this contains the signature value of the canonicalized signed info element. So what's the signed info element, you might ask? And that's the only element in this whole document that's directly protected by the private key signature. And it describes its own canonicalization method, as well as the algorithm then used to generate like the signature value. So this would be the, something like RSA or so. And so what's canonicalization? And that's like a normalization feature. And the designers of XML signatures decided that they want to make these signatures robust against syntax changes in the XML document. So if you introduce like comments or white spaces or new lines that don't change the meaning of the document, the signature should still work. So they can't like just simply sign the byte stream of the document. Instead, they have this additional normalization step where they like generate like a normalized form of the XML document and then do like the signature on this form. And this normalization step is like, again, a very nice source of authentication bypasses. It's also one of the bigger mistakes in the standard, but we don't care too much about it. Instead, we want to look at the reference element. And reference elements are used to extend the integrity protection of the signed info element to other parts of the document, or like for example, the outer response or the assertion element, so the stuff we actually care about, right? And a reference identifies the data it protects using a URI. And again, in the ideal world, this would be a response or an assertion. And then this is kind of like where it gets exciting. It specifies a number of transforms that get applied to the reference data. So the idea here is, hey, we signed this plop, but we don't actually want to like check the signature on this plop. Instead, we like randomly transform this data first and then check the signature on the outcome. I'm still not sure why you actually need this, or like at least why it's so configurable, but it has some use cases. So transforms that are supported are basically, again, like the normalization. You have something called like the enveloped signature transformation, which basically removes the signature out of the like verified document. And if you think about it, that absolutely makes sense, because you can't calculate a digest if you have like a changing signature in there, right? But then you have like the more surprising ones. You can do like base 64 decoding here. So you have like a base 64 encoded plop, you decode it, and then you calculate a hash digest on this decoded plop. And you can also do stuff like XPath filtering and XSLT, which I don't think there's any reason why this is in the standard, and I still haven't been able to come up with a good use case for this, if you're not an exploit developer, as we will see later on. So you execute all the transforms, then you have like the hash of the end result, and you compare that with like this digest value. If they match, you can be somewhat sure that the data you just looked at is the data you expect or you signed. I mean, depending on your transforms, it might be something completely else, but you get the basic idea. So what's up with these transforms, right? Like, are they actually part of our remote attack surface? And the answer is it's somewhat complicated. So if you verify such a signature, you can split it into two parts, the signature validation and the reference validation. So for the signature validation, you need to verify that the signed info element is correctly signed and that this signature was created by a trusted key. For reference validation, you actually go through all the reference data, push it through this transform chain, and check the digest at the end. So from a theoretical standpoint, it's completely irrelevant in which order you do this. But from an attack surface standpoint, it's very important because if you do a reference validation first, which interestingly is the recommendation in the RFC, then the whole transform chain can be written by anyone, right? Like it can be completely malicious and it's part of your attack surface. The other step is you can do a check on that signed info is correctly signed, but the A.2 step, if this is signed by a trusted key, if you do that after reference validation, which is surprisingly something like a lot of applications do, you're still part of the unauthenticated attack surface. And the interesting part, and this is why this is becoming more relevant for cloud, if you have a multi-tenant service provider where like customers can provide their own identity providers, this is always part of your attack surface, right? Because I can just configure my own malicious identity provider and they can always survive the signature validation step. So regardless of the ordering, you will be able to attack this. And then, which is also interesting, because identity providers are kind of valuable, service provider attacks in the direction of the identity providers are also possible if the IDP actually validates signatures. So in practice, this is basically part of the attack surface for pretty much anything we care about. So let's look at some bugs you actually find when you poke at this. So this is the first issue is pretty straightforward, vulnerability. So this is part of the .NET standard library when you do signature verification in .NET. So when you chain multiple of these transforms in an XML signature, .NET will first run the transform, then it reparses the output, so which will hopefully be XML again, with a new XML reader object. So if you have like a base 64 decode transform, you have this plop, .NET will decode it and then pass the result. And the fun part about this is that this internal XML reader that's like only visible in the standard library is configured completely insecurely, right? It enables DTD processing and it also allows you to resolve external entities that point to the network or the file system. And you can use this pretty easily to basically exfiltrate arbitrary local files or internal URLs when a .NET application passes a signature. So you can do this with like an authentication request to a SAML-enabled .NET application. And the example payload is really, it's pretty simple, right? Like here you have like some fake response element, you have this base 64 plop, you specify a base 64 transform in the middle of the signature. On the left side, you can see what the base 64 is actually meaning, like if you decode it. And then basically on the right side, you see like how you can use this to basically exfiltrate arbitrary files from the file system. So it's pretty straightforward. It's a really basic XXE attack. But because the vulnerable code is inside the .NET standard library, it affected pretty much any .NET application that I looked at that supported SAML. And I guess one interesting thing about all of these bugs is they are not really SAML specific, right? They are XML signature specific. So if you have some other application, like a weird e-banking protocols, for example, that rely on XML signatures, you can basically take the same bug and exploit it. So if you remember the list of supported transform algorithms, one in particular looked quite interesting, right? And that's XSLT. So XSLT is a full programming languages that uses XML for its syntax. And it is designed to transform or combine XML documents from one form into another. And it looks a bit intimidating at first, especially if you're too young to ever work with XML professionally. It actually has most of the features that you would expect from a programming language, right? Like you can do loops, you can do branches, you have function calls, and a somewhat limited standard library. And the example on the left basically shows a really simple XSLT program that just iterates through all data elements in an input document, extracts the first character, and then puts it in an output document. And I mean, so if you're like a security researcher and you look at this even for 5 minutes, you probably realize that this is not something you want to have in your external attack surface, right? Like especially like pre-auth. It's like a full-blown language runtime that you can interact with without like any form of interaction or authentication. So if you find something like this in a protocol, you of course want to see how this is actually implemented. And the first project I looked at is the XML signature library, XML security library, which is also known as XML-sec. And XML-sec is the go-to C implementation of the XML D6 standard. So a lot of like the high-level SAML implementation, so if you want to write a high-level Python implementation of SAML, you will use bindings to this library to perform the actual signature validation. And one example here is Python 3 SAML, which is like probably the most popular Python implementation of the protocol. And like if you actually like step through how the call stack of this looks like in the end, it's kind of fascinating. Because of course XML-sec, they don't implement their own XML parser or XSLT engine, right? Instead, they rely on libxml2 and libxslt for implementing this. And both of them are pretty like old and solid C code bases, so you find like all the nice memory corruption stuff that you would expect from this. Like libxml2 is kind of reasonably well fussed because like it's part of the attack surface of basically everything that touches XML. But the ability to actually like generate XML dynamically using libxslt, right? Because now you get like a scripting interface added on top of libxml2, gives you like quite a lot of options, and you end up with the ability to trigger quite obscure memory corruption bugs like deeply hidden in this XML stack. And you can trigger all of that using like a GET request to the right URL on like a SAML-based application, right? So one fun example that I found during this research is a heap buffer overflow in libxml2. And it's a pretty standard integer overflow where you can do a controlled out of bound write. But to trigger it, you need string buffer sizes which are close to the maximum value of a 32-bit integer, right? So you need like a string that's like 4 GB in size. And this is not something that's part of, I mean, normally, like if you use libxml2, you're probably not too worried about this because you're not going to pass random 4 GB blobs of XML. But libxsl2 actually makes it possible to generate these inputs completely dynamically, right? Like you just have like a loop that, I don't know, concatenates strings, and after it runs for a while, you get like this large string. And then you get like a pretty controlled out of bound write when like this size condition, like you skip over the reallocation and instead directly do like this mem move. And normally I would spend the rest of this talk talking about how you can turn this issue into an exploit, because it's actually pretty fun, right? Like you can corrupt the state of libxsl2, then you have like some interactive runtime corruption, and it's quite a fun challenge. But actually I found one more bug, and I think this has to be my favorite bugs for quite some time, that I find even more fascinating. So instead I'm going to talk about this one. And this one, like it's an integer truncation issue in a software component called XSLTC. And XSLTC, I hope you haven't heard of it before, because I definitely didn't, is an XSLT compiler. And it originally was part of the Apache Xelen project, but then it ended up in the Java standard library via a forked version. So now it's like part of OpenJDK. It's the default runtime for XSLT in all major Java versions. It turns out that this thing actually takes XSLT to provide to it, does a just-in-time compilation into Java bytecode, and then runs this bytecode, right? So this means that you now have like a just-in-time compiler as part of your remote server-side pre-authentication attack surface, right? Which again is something you probably don't expect if you just install a SAML auth library on your web server. So Java in theory has like a config flag where you can like disable XSLT in XML signatures, right? So you can say, hey, I don't allow XSLT. Which seems like a good choice, but it's defaulted to off until JDK 17, which is like 1 year ago. And if you know Java, you know almost no one is actually running anything that's more recent than JDK version 11. So in practice, like this is enabled in a lot of places. So XSLTC is a pretty complex project. It has like a lot of fascinating code in there, but the bug is actually quite simple. So when XSLTC compiles the XSLT template into a JVM class, it translates all the strings, integers, and floats that you put in your XSLT script into JVM constants, right? So you create like a real JVM class. The problem is if you actually look at the class file format, so this is like the header is shown on the left side of the screen, you realize that the size of this constant pool is specified with a 16-bit integer, right? So a JVM class can normally only have around like 65K constants. And the problem is that like in this whole stack, XSLTC does not enforce this limit in any way. And even better, if you look at the code on the left side, on the bottom left side, which is like responsible for serializing the internal compiler state into a Java class file, you can see that they will simply truncate. So this constant pool Java variable that you see in the bottom is just like a normal Java array, right? So this length is actually like a 64-bit integer. But they just dump a short to the disk or to the file. So what happens here is they will just truncate it. But then they will still iterate through the whole array and dump the full attacker-controlled constant pool into this class file. So what you get with this is a primitive I call constant pool overflow, right? And part of our attacker-controlled constant pool will now be interpreted as the JVM class fields stored behind this pool. This includes stuff like the access flags of the JVM class, but also method definitions and their bytecode, right? So the goal we have is to use this corruption to create a valid JVM class containing arbitrary bytecode, because then when the XSLT runtime thinks, hey, the compilation was successful, let's load this class, we're going to actually execute whatever we want. So to understand how we can actually do that, we need to look at the actual content of the constant pool. So JVM supports around 12 different constant types. They are stored in the pool and are like specified using a single byte tag, followed then by the actual objects. And as you probably can expect, like most of these are pretty difficult to generate using like our XSLT input. But the 4 types you see on the left side can be pretty easily generated, like they correspond one-to-one to like stuff you put in your XSLT. So we have 32-bit integers, we have a double floating number, and we have 2 types related to strings. So a UTF-8 info is actually the constant entry that holds the raw character data. Whereas string info is then like a pointer indirection. So like this string index field in the string info element points to a corresponding UTF-8 entry. So normally this would be like the perfect primitive, right? The UTF-8 entry, it's like variable sized. We can like put string stuff in there, so that looks pretty straightforward. Unfortunately, it's not really useful for us because like JVM uses some weird encoding scheme and for this UTF-8 content, and most importantly, we can't put null bytes in there, right? So it's not possible to have a string with null bytes on the JVM level. This means we won't be able to fix up all like these size fields that we see later on, so we can't really use them. Instead, we rely on double entries as our core corruption primitive, because doubles, like if you ever did JavaScript exploitation, you're pretty familiar with this. You basically get 8 bytes of almost like completely controlled content. Here in the JVM world, we always have like this single 6 byte in front that specifies the double type. But we can see later how we deal with this or if this is a problem. So before we reach the interesting parts of the class definition, we need to overflow 3 header fields with valid values. And all of the stuff in the JVM is big endian, so remember that when we later talk about the actual stuff we put in there. So access flags is a mask of flags that describes the access permissions and the properties of our Java class. And if you know Java, it's stuff like public, private, or abstract in your Java code, right? And we need to make sure that the class is actually public and is not abstract and is also not an interface, because otherwise the XSLT runtime won't be able to load it and our exploit will fail. We then have this field, this class, which is again an index into the constant pool. And it has to point to a constant class entry, which describes the class of the file. Fortunately, there are no real requirements on this. Like you can just put it at some arbitrary class entry that the XSLTC compiler puts in the constant pool, so we don't need to worry too much about it. A superclass is a bit trickier. It's another index into the constant pool. And it describes the parent class of our class, right? And XSLTC actually has a check on this, so it needs to be identical to a class called abstract translate. So we really need to have full control over this index to make it point at the right spot in the constant pool. So one important thing about this bug is that we can't fake entries in the constant pool, right? Like we need to basically invoke the right functionality of the XSLTC compiler to put these constant entries in the pool. Fortunately, most of the time that works pretty well. We then just need to ensure we actually use the right indexes to point to the pool. So the first thing you actually run into pretty much as soon as you start this exploit is that we can't use our double entry for the access flags field. And the problem here is that the first tag byte of our overflow always ends up in the access flags field. So the 6 from the double type will always be part of the access flags, and this results in an abstract class, which we can't use. So we can't use doubles as like the initial start of our overflow. And then you end up with like pretty weird tricks, but basically what you have to do is you put hex 10,703 elements in the constant pool. So you have like a lot of constants in your XSLT input. This will get truncated, so you will only have like a constant pool count of hex 703. And the index, or the element at that index will actually be the one that overrides the access flags field in the header. If we align everything correctly and then put a const string entry at this specific spot, it will actually point at like the preceding offset, because if you remember, like string info and UTF info, they are like pointing to each other. And we end up with a situation as shown here. So we have a const string entry, which overrides the access flux. And so we get a value of hex 08, hex 07. The first byte comes from the tag. The second part is part of the UTF-8 entry reference. And the good thing about that JVM is that it pretty much ignores everything it doesn't understand. So if it sees like a value like that doesn't match to any flags it's know, it kind of ignores them. The only thing it cares is that the lowest bit is set, because that's the flag value for public. So we end up with a public class. So we can continue. We want to point this class to something in the exacting constant pool, right? So what we can do is we just put a constant double as like the next entry in our overflow. We now get this class value of hex0, hex02, hex06. And it just points somewhere in the constant pool, and we need to make sure that there's a class entry at this point, but that's relatively straightforward to do. And then finally we end up with like full 8 bytes of controlled double payload. It's not completely controlled, but mostly. We use this to specify the superclass. If you remember, that was the one where we need to be pretty careful to point to the right class. We can completely skip interfaces and fields by just putting like a length of 0 in there. So we skip over these tables because we don't actually need them for code execution. And then finally, we still have 2 bytes to define the method counts, which is the stuff we want to actually exploit. And from there, it's actually relatively straightforward. Like you need to wiggle a bit around with all like the offsets and stuff. But if you look at how methods are defined in the class file comment, in class file format, we only care about a couple of things, right? We want to create a fake constructor method for our class, which will then get executed when the XSLT runtime actually instantiates our class. So we need a method that has, again, a public access flags and the right name and type. The interesting part about the JVM is the actual code of the method is somewhere hidden in this attributes table. So if you have like an attribute that's actually named code, then it gets interpreted as this data structure on the right side, where somewhere in the middle you actually can put the real JVM bytecode. So everything else is kind of irrelevant and you can basically just knob it out. The trick we do here to put our own bytecode in is that we actually define 2 methods. The first one is pretty much useless and doesn't have any code, but we can use like the dynamic sizing of these attributes tables so that everything aligns perfectly for our second method header, and we can fully control that again. And then we just need to like put all the right offsets in there, all the right indexes, and we get a fully controlled or almost fully controlled bytecode payload with like the double entries at the end. So the interesting thing here is that you get 8 bytes of controlled Java bytecode, and then you get again one of these tag bytes, right? Like the 6. So at the beginning I was nervous that this would break stuff. But we get lucky here because from a JVM perspective, the byte 6 corresponds to a push the integer 3 on the stack instruction, which is pretty much the perfect instruction to have in the middle of your payload, right? Because you can just work around, you just pop it again and you don't care about it. So this means pretty much we can easily like put our own JVM bytecode in here. So one interesting thing about JVM bytecode is in itself it can't do much interesting stuff. So you still need to create entries to the classes and methods you want to call in the constant pool, right? Because in Java bytecode you have something called function add constant pool entry, whatever. So we can't fake our own entries, so we need to find a way to make XSLT actually emit those. Fortunately, XSLTC has this Java extension feature, which means if this feature is enabled, you can call arbitrary Java methods. Of course, that's completely insecure. Like if this feature would be enabled, we don't need the exploit, right? And it's always disabled when you do XML signature validation. But the interesting thing here is this disabling of the feature is done with a runtime check in the compiled application. So the compiler will still put like these method and class references in there. It's just when you want to call them in your final runtime, you always run into a check. So this means we can just like use this extension to call like an exec function in Java lang runtime, and then this code never actually runs, but then we can like use these class references in our own bytecode to actually run the code. There's two more things we need to fix. One is the constructor type check. So we fake our own Java constructor, and the JVM will complain that this constructor doesn't actually call the constructor of the superclass, right? Because that's a pretty fundamental thing the JVM expects to happen. But we can bypass that check by just throwing an exception at the end of our constructor, right? Like, because then JVM sees that this function never returns, so it's kind of happy with it. And then we have like the whole rest of the real XSLTC output, so the normal code that gets generated. But we can just skip about this with one of these dynamically sized attributes that you saw in the file header. So you just need to make sure there's no garbage at the end of the class file, otherwise JVM will complain. So that's pretty much it. Then you have like, so this is like a snippet of the exploit where you can see basically you write doubles to do all of the stuff, and then you get like your bytecode. Normally I would show you a demo how this exploit works. It's pretty boring actually, but I also broke my demo this morning, so I apologize for that. But part of Project Zero, the nice thing is you can actually check out the full exploit for this, right? So you don't need to trust my demo skills. Instead, you can go to our issue tracker and actually look at the full exploit. It contains a couple of tricks that I skipped over, but it's pretty good documented, so I hope you enjoy it. Yeah, some final conclusion before I wrap up the talk. So SAML and XML DSEC in particular offer a large and complex attack surface to external attackers. So there's still a lot of bugs hidden, so you can expect some more follow-up publications on this. Multi-tenant applications change the threat model for this whole attack surface and makes these attacks more relevant for modern cloud environments. And I think this is something for all the exploit developers in here. You can find really interesting weird machines even in memory-safe languages. So I guess even if the whole world moves away from memory unsafe code, we can still find stuff like this and have fun. So thanks for listening. If you have any questions, you can reach out to me via Twitter or email. I also want to give a quick shout out to Matthias Kaiser and Thanatos. So Matthias is a security researcher who actually noticed the OpenJDK bug and then wrote in his own exploit in the time span it took us to release the proof of concept. So it was quite impressive. So heads up to Matthias here. Thanatos is a Chinese researcher who published a super detailed write-up for this bug after we derestricted our issue tracker entry. So it was also quite impressive and great to see. So thanks to these two guys for working on this. That's it. Thank you.